Hello, welcome to the class of Advanced Stats and Econometrics. In today's lecture, we are going to discuss the regression diagnostic one, that is multicollinearity, and then we will move further from that and we will look at different problems. So, multicollinearity. What is a multicollinearity? So, one of the assumptions of classical linear regression (CLRM) is that there is no exact linear relationship among the regression. If there are one or more such relationship among the regressor, we call it multicollinearity or collinearity for short. Perfect multicollinearity, perfect linear relationship between two variable exists. If it is existing, then we call it as perfect multicollinearity. Then you cannot estimate the model. Imperfect collinearity, the regressors are highly collinear but not perfectly collinear. Then it is called imperfect collinearity. Consequence: if collinearity is not perfect but high, several consequences ensue. First is the OLS estimators are still blue, but one or more regression coefficients have large standard errors related to the value of the coefficient, thereby making the t ratio small. Even though some regression coefficients are statistically insignificant, the R square value may be high. Therefore, one may conclude that the true values of these coefficients are not different from 0. Also, the regression coefficient may be very sensitive to small changes in the data, especially if the sample size is relatively small. Variance inflation factor. For the following regression model, yi is equal to b1 plus b2 times x2i plus b3 times x3i plus ui. It can be shown that variance of B2 is sigma squared upon summation x2i squared times 1 minus R23 square, and R23 is the correlation coefficient between x2 and x3. So sigma squared upon summation x2i squared times VIF, and variance of B3 is similarly sigma square upon summation x3i square times 1 minus R23 square. So sigma square over summation x3i square times VIF, where sigma square is the variance of the error term ui, R23 is the coefficient of correlation between x2 and x3. Variance inflation factor is equal to 1 upon 1 minus R23 square. This is the variance inflating factor. VIF is a measure of the degree to which the variance of OLS estimator is inflated because of collinearity. Direction of multicollinearity: high R square but few significant T ratios. So if you are supposed to detect the multicollinearity, how can you detect whether multicollinearity is present in a model or not? So you can see that these are some of the symptoms. If they are present, then multicollinearity is likely to be there in the model. So highest R square but few significant T ratios. If this is the situation, then most likely it is due to the multicollinearity. High pairwise correlation among explanatory variable or regression. High partial correlation coefficient. Significant F test for auxiliary regressions of each regressor on the remaining regressor. High variance inflation factor VIF, particularly exceeding 10 in value. And low tolerance factor TOL is the inverse of the VIF. Remedial measure: what should we do if we detect multicollinearity? Nothing, for we often have no control over the data. Second option is redefine the model by excluding variables that may attenuate the problem, provided that we don't omit relevant variables. Third option is principal component analysis. Construct artificial variables from the regressor such that they are orthogonal to one another. These principal component becomes the regressor in the model, yet the interpretation of the coefficient on the principal component is not as straightforward. Regression diagnostics 2. So that is heteroscedasticity. Remember, one of the assumptions of the classical linear regression model is that you have a homoscedasticity or variance is constant. But if that is violated, we call this as heteroscedasticity. So one of the assumptions of classical linear regression is that the variance of ui, the error term, is constant or homoscedastic. The regions are many, including, so the region for the heteroscedasticity are many. Some of them are presence of outliers in the data. If you have outlier, which means values are extremely high or extremely low in the data, then this may cause heteroscedasticity. Incorrect functional form of the regression model. If the functional form of the regression model is different from what you are assuming, then you might get the problem of heteroscedasticity. Incorrect transformation of data. If you have not properly transformed the data, then you might face the problem of heteroscedasticity. Mixing observation with different measures of scale, such as mixing high income household with low income household. Consequences. If heteroscedasticity exists, several consequences ensue. The OLS estimators are still unbiased and consistent, yet the estimators are less efficient, making statistical inference very uh, less reliable. The estimated t-values may not be reliable. Thus, estimators are not best linear unbiased estimator blue, they are simply linear unbiased estimator. In the presence of heteroscedasticity, blue estimators are provided by the method of weighted least square. Detection of heteroscedasticity. One approach is to graph histogram of squared residuals. Second is to graph squared residual against predicted y. Third is Bruce Pagan test. Fourth is White test of heteroscedasticity. And then there are other tests such as Park, Glaser, Spearman rank correlation, and Goldfand quant test of heteroscedasticity. So Bruce Pagan test or BP test. So estimate the OLS regression and obtain the square OLS residual from this regression. Regress the square residual on k regressors included in the model. You can choose other regressors also that might have some bearing on the error variance. The null hypothesis here is that error variance is homoscedastic. That is, all the slope coefficients are simultaneously equal to 0. Use the f statistic from the regressor with k minus 1 and n minus k in the numerator and denominator degree of freedom respectively to test this hypothesis. If the computed f statistics is statistically significant, we can reject the hypothesis of homoscedasticity. If it is not, we may not reject the null hypothesis. White test of heteroscedasticity. Regress the squared residual on the regressor, the squared term of the regressor, and pairwise cost cross product term of each regressor. Obtain R square value from this regression and multiply it by the number of observations. Under the null hypothesis that there is homoscedasticity, this product follows the chi-square distribution with degree of freedom equal to the number of coefficients estimated. The White test is more general and more flexible than BP test. So what are the remedial measure if you find heteroscedasticity? What should we do if we detect heteroscedasticity? Use method of weighted least square. Divide each observation by the heteroscedastic sigma I and estimate the transformed model by OLS. Yet true variance is rarely known. If the true error variance is proportional to the square of one of the regressors, we can divide both sides of the equation by that variable and run the transformed regression. Second is take natural log of dependent variable. Third is use white heteroscedastic consistent standard error or robust standard error. So that is valid in large samples. And the reference for all this is a book titled Econometrics by Example, second edition. Publisher is Palgrave Macmillan and the author is Damodar Gujarati. That's it for today's class. Thanks.